ROS developers, and welcome back to the open classes. Welcome back to a new open class. We are today in open class number 204, if I'm not mistaken. So we've got some weeks without open classes. Don't worry, because we are going to be launching an interesting new thing. I don't want to make any spoiler soon, which we have been working on in the last weeks. But yeah, so now we are back with a regular schedule. We are going to be having again our open classes every Tuesday at 6 p.m. CET. So yeah, get ready for learning a lot of robotics and ROS. Then yeah, so welcome back. Today we have open class number 204, as I was saying, and the main topic for today's class is how to measure robot movement. We are going to be seeing different approaches of how to do this, and with some practical examples using different sensors. So I'm sure it's going to be really interesting, and we are going to provide you lots of code so that you can keep working and learning and improving the project. So yeah, let's get started. Let me know if everything is fine, as always. First of all, I think everything is good, sound is good, image is good. So I'm going to already switch to my computer screen here to have the chat ready. Then let me go myself to the open class, where it should be, around here. There we go. Okay. Hi there, long time no see, says Gilbert. Hello, hello Gilbert. Hello Joel from Virginia. Hello. Okay. So since nobody is saying anything, I will assume that everything is fine. You can hear me properly. So yeah, then let's not lose any more time. And let's get started. So let me just real quick remind the usual procedure that we follow in open classes in case that we have some new people here. Then our open classes are always focused on practice, okay? So this is not a class where I am supposed to be talking and showing things, and you just sit there listening and watching to what I am explaining or doing. That is not our type of classes. In our classes, we want you to practice live alongside with me, in this case, right? Then for this, what we always do in our classes is to prepare a ROSJECT. All right, a ROSJECT is a web-based ROS project that can be very easily shared with anybody. And in this case, in order for you to get a copy of this ROSJECT, all you have to do is to click on this button that appears right above the chat here, which says fork and open the class ROSJECT. Okay. Then by clicking here, this is going to create a copy of this specific ROSJECT in your account, a permanent copy, right? So let me actually click myself here to get my own copy and to show what's going to happen once you do that. So once you click there, first of all, what's going to happen is that you are going to be redirected, as you can see here, to the main ROSJECT page, okay? It's going to take a few seconds to completely load the whole environment. Okay, that is normal, don't worry. And then also here in the right side, you are going to still find the stream panel, let's say, with the video feed, also the chat, in case that you want to type any question, comment, feedback, whatever you want. You have it here. In my case, what I'm going to do is to remove it from my main ROSJECT screen so that I have more space here to show what I'm going to be doing. And then right here, I'm going to just leave this opened to be able to read the chat easily. All right. Then, as you can see, this is going to redirect you to the main project page. And then also, as I told you, this is going to create a copy of this project in your account. What does this mean? This means that you are going to be able to access this project whenever you want, not just for today's class, but in case that you want to access it next week, next month, whenever you want, you are going to have it in your account. All you have to do is to go to the My ROSJECTs area here in the left menu. Yeah, and then if you go here, if you open this My ROSJECTs area, here is where you are going to find all your ROSJECTs, and of course this one, which is the one that you have just copied now for the class. All right, so this you are going to have it for ever in your account. All right, then let me go back here to the main ROSJECT page. So after a few seconds, when the environment finishes loading, you are going to have something like this. Yeah, this is the main ROSJECT page, and you are going to have here automatically opened the notebook for today's class. Yeah, this is the notebook with all the contents, explanations, sample codes, everything that we are going to be following during today's class. You are going to find everything here. Okay? All right, then so far so good. Has everybody been able to get their ROSJECTs opened? Yes, no? Any issue so far? All fine, yes, yes. All good. Okay. Excellent, excellent. So, everything is fine, everybody is ready to get started. Okay, then, what's the topic for today's class? Well, the topic for today's class is how to measure robot movement. Yeah, this is a very important topic in robotics because it's really important to keep track of how much and in what direction, how many meters a robot has moved, right? This is very important, especially for mobile robots, yeah? Robots that are moving around an environment. I am thinking maybe a warehouse. Yeah, it's very important for robots to be able to keep track of their own movement, so that they are able to know where they are in the environment at any time, and they are also able to avoid obstacles, etc., etc. So, for today's class, we are going to be focusing on how to measure robot movement. We are going to be seeing several practical examples of how to do this, how to achieve this using different sources, yeah, different sensors, let's say. All right? Then for this, we are going to be using, as we have been doing lately, our BotBox robot. Yeah, the BotBox robot, probably you already know it, but let me just refresh this for all of you, is an robot kit that we provide at the Construct, which is very convenient for teaching. Yeah, you can see an image here at a university, and it includes a real robot lab with 3 different robots, but it also includes robotics courses and several practical projects ready to be used and to be delivered for your students. Yeah, covering several topics from basics to navigation to perception, etc. Yeah, all this is included in the BotBox kit, robot kit, and it is especially designed to provide hands-on practice-based robotics classes with minimal preparation and maintenance. Yeah, we at the Construct always want to teach and to put all the focus on teaching by doing. Yeah. So everything that we provide, we always put the focus on being hands-on and practice-based, as right as these open classes, right? Then this is the contents of the BotBox warehouse kit for campus for universities. It includes 3 robots. It includes also the warehouse floor map, with several interesting features, all the plastic wall panels in order to properly mount the warehouse environment, as you can see here in the real life picture. It also includes grippers to perform manipulation tasks, some cubes with QR codes in order to be able to practice also perception-based projects. As you can see, it also includes several already prepared ROS projects that can be directly used, and also some course material and students management panel, so that you can properly manage the access of all your students to the courses, to the projects, and to the lab. And in case that you want to learn more, as here you can find a link to the BotBox Warehouse Lab webpage, so that you can get more details, and in case that you are interested, you can order one for yourself. All right, then with the proper introductions being made, let's get started with the class. And we are going to start by introducing this concept of measuring a robot's movement. Yeah, then this is very crucial. Here we have a very interesting image where we can see that properly being able to measure a robot movement is going to affect directly into having an optimized performance, of course, yeah. Also to enhance safety, because the robot is going to be able to better avoid dynamic obstacles, yeah. Let's imagine a robot which is moving through a warehouse, an industrial environment with people around the warehouse, yeah. Then the robot has to be able to detect in real time the people that is moving around the environment, and it has to be able to avoid them, right? We don't want a robot to be crashing against the workers, the people who is there in the warehouse environment. So yeah, this is obviously achieved through being able to properly localize itself in the environment, yeah? And for this, the robot needs to be able to track its own movement, to be able to measure its own movement, yeah? And obviously, in order to provide an effective navigation, yeah? So that the robot is able to move from point A to point B, yeah? To generate a plan and to, especially to be able to follow this plan, this planet path accurately, the robot has to be able to track and to measure its own movement, yeah? Then there are many different ways in which this can be achieved. Here we have some common approaches. Odometry is one that probably most of you already know. We have been using also this topic in several classes, yeah? So this is the odometry of the robot is the foundational method that uses wheel rotations or joint movements to estimate changes in position over time. Yeah, usually in robotics, the most basic odometry is computed using wheel encoders. Yeah, which we are going to see this approach in a moment. So yeah, odometry, a very, very important topic, which is used in ROS, and it's used in order to track the robot movement over time. Yeah. Other very interesting methods are, for instance, RGB camera image analysis. We are going to be seeing a practical example of this, yeah? So the robot, in case that it has an RGB camera on it, which is a very typical case, also even for basic robots. For example, these ones, the tortoise bot that we provide in the BotBox Warehouse Lab, have RGB cameras on them, yeah? Then cameras can also be used in order to track movement by comparing the differences between the different images that the camera is capturing, yeah? Finally, twist commands. Twist commands also, probably most of you have heard about these twist commands or even twist messages that are used in ROS in order to send velocities to the robot, yeah? In order to send velocities to the wheels of the robot, for controlling, for moving the robot. These twist commands can, of course, also be used to measure the expected movement of a robot. Yeah. Laser scans also another very typical sensor used in robotics, also known as LIDAR, yeah, can of course also be used to track movement by comparing previous readings with current readings, checking the difference between readings, between laser readings over time. We can also approximate how much the robot is moving. Yeah, we are also going to see a practical example of this during this class. And finally, sensor fusion, which basically allows us to combine, to fuse several of these methods or several sensors, combine them in order to have a much more accurate track or measure of the robot movement. Yeah. For example, the odometry method, or let's say tracking the robot's movement using wheel encoders, is a very extended method. Probably it's the first one which almost any mobile robot is going to have, yeah? But it has some problems, yeah? It usually tends to accumulate error over time due to wheel drifts, yeah? And then in order to fix this, we can use this wheel encoders information and combine it with others, yeah? For example, with laser information, with even other sensors, such as GPS sensors, yeah, that also allow robots to track their position over time. Yeah, and then by using this sensor fusion method is how we are going to be able to achieve a much more accurate or precise position of the robot's movement over time. Yeah. Yeah. Does all of these make sense? Is everybody following? Yeah. Does this sound familiar to you, to all of you? What I am talking about? Yes. Okay, I can see that most of people, yeah, is familiar with all these concepts. Excellent. Then let's continue. All right. Yeah, so here we have some real-world examples that I have already been discussing some. For example, warehouse automation, yeah? The typical scenario where we have a robot which is moving around the warehouse, maybe moving packages from one place to another, from etc. Yeah, these kind of robots are already out there in the industry and they are being used. And for this kind of robot, it's crucial to be able to track their movement. Right? Another very common example is autonomous vehicles, yes, self-driving cars. Also super important for them to be able to track the movement. And for example, in autonomous vehicles, a very typical sensor is GPS, yeah? Is very commonly used in autonomous vehicles for tracking their position on the roads, yeah? And finally, also exploration robots, yeah? This can be, for example, underwater exploration robots or even extraterrestrial exploration robots that we can send to the moon, to Mars. We already have robots there, which we use for moving around the environment, getting samples of the terrain, etc. Yeah. Also, these robots have to be able to know where they are. Yeah, and they have to be able to track their own movement so that they don't get lost. Yeah, if we send a robot or to Mars and we wanted to explore the terrain and get samples of the terrain and bring it back to a station for analyzing it. Yeah, for all of these, we need to be able to track the robot's movement and to know where it is going, and how to make it come back to the main station so that we can then get the samples and analyze them, etc. Yeah, so many different scenarios in robotics need this feature. And need the robots to be able to track and measure their own movement. All right? Then, We are going to start by probably the most basic one, which is wheel encoders, yeah, and odometry, all right? So, how does this work? Well, it's pretty simple, yeah? Basically, wheel encoders measure how much a wheel is spinning, yeah? So as a wheel spins and rotates, yeah, these encoders measure the number of pulses per revolution of the wheel. Yeah, one revolution is a complete revolution, a complete, let's say, spin of the wheel. Yeah, then for each of these, the encoder registers pulses. Yeah. Then using these pulses and getting some additional information, such as the radius, the circumference of the wheel, we can compute how much a wheel has spin. Yeah? And then using this information, we can estimate how much the robot should have moved. Yeah? We use some formulas for computing this. Here you can see the distance per pulse, for example, which is 2 multiplied by pi, multiplied by the wheel radius, divided into the pulses per revolution. Yeah? So by multiplying the number of pulses by the distance per pulse, we can determine the distance traveled by a specific wheel. Yeah? This is how wheel encoders work and how they can be used for tracking a robot's movement. Yeah. Then here you have an example, sample example code. I'm not going to execute this one because it's just a very basic example, okay, and we are not even applying it to the robot. But here you have a very basic structure of how to compute using wheel encoders the movement of a robot. Yeah. So we would need some information. Yeah, for example, the wheel radius and the pulses per revolution, yeah, which can be different depending on the encoders that you use. And then using some formulas like the one that we have introduced here, the distance per pulse, yeah, we can get how many pulses each wheel has, and then we can compute with this how many distance each wheel has traveled, yeah. And then, for example, for a differential drive robot, which is the case of the tortoise bot robot that we have in our BotBox warehouse kit. Yeah, if the robot is a differential drive robot, then we can compute the average distance by adding the left wheel distance plus the right wheel distance and dividing by 2. Okay. So this is a very basic example of how to use wheel encoder to compute a distance moved by a robot. However, I want to create a more practical example here by using the simulated robot, okay? Then for this, we have this example code here that we are going to be running in a moment in the simulation of the BotBox environment, yeah? Then for this, let's everyone start by launching the simulation. Yeah. Here you have the first the commands that you need to run in order to start the simulation. All right. So all of you, right below here the odom distance Python script, you have the instructions to start the simulation right here. Okay. Then let's execute these commands in order to start the simulation. So for this, obviously, we need a shell, a terminal, where we can execute the commands, right? So for this, it's very easy. All you have to do is to click on this icon here that you are going to find in the bottom menu, right here, which says Web Shell. Yeah? So if you click here, you are going to see that a new terminal is going to appear like this. Yeah? And this is a regular Linux terminal where you can execute commands. So we are going to execute these 3. Yeah? You can copy all of them directly here through the notebook with this copy button. Yeah? And then this is going to copy and paste the 3 commands. The first one is just a script to clean any Gazebo process that is running so that we start Gazebo from 0. Second one, of course, we are sourcing here this specific ROS to workspace where we have the packages, files, everything for our simulation. And then finally, we have the ROS to launch command that is going to start the BotBox simulation. Yeah. So if I press enter here, all the processes are going to get started. And after a few seconds, you all should see a Gazebo window popping up here. So let's wait for it to appear. Yeah. It should appear automatically, okay? Sometimes the first time that you initialize the simulation, it takes a bit longer, okay? Because Gazebo takes a bit longer to load. Then you can also manually click here in case it doesn't appear, okay? In this icon here, which is next to the Jupyter notebook. Yeah, this is going to open the Gazebo window manually. And then here is where we should see the simulation appearing. There we go. Okay. Let me move around here so that I can have a full view of the environment. And here I have the simulated version in Gazebo of the BotBox warehouse kit with the TortoiseBot robot right here. All right. Yeah. Has everybody been able to properly start the simulation? Yes, no? If you are having any problem, let me know, okay? Yes, yes, yes. Lots of yeses. So I understand that everybody has been able to start their simulations. Excellent. Okay, awesome. Then we are ready to continue. Okay, so now we have our simulation running here. And then what we are going to do is to open a second terminal. Okay, how? Very simple. You just go here to the one that you already have opened. And if you click on this plus icon, yeah, this is going to allow you to create and to open a new terminal. Yeah, there we go. Here we have a second terminal. We are going to leave this one here running because if we close it, obviously the simulation is going to die. And we want our simulation running. So let's open a second terminal. And then here, what we can do is what we are going to do is to execute our script, okay? But before that, we need to create the script, yeah? Here you have the steps. So we are going to go inside our ROS to workspace SRC folder, and we are going to create this odom distance.py, yeah? Again, what you can do is to copy the commands directly here and then execute them in the terminal. So cd ROS to workspace SRC and then touch, and we create the new Python script in the path. Yeah. So if, for example, I run ls, here I can see my file. Additionally, now that we are going to start creating new scripts and copy pasting code to these scripts, I suggest that all of you open the graphical code editor, okay? How to do that? Very simple. It's the icon which is right at the right side of the terminal icon, yeah? First icon here is the one for the terminal, for opening the terminals. Second one is the code editor icon. So if you click here, this is going to open the code editor, okay? Then with this code editor, you are going to have access using a graphical interface to all the different workspaces, files that you create, etc. Here, yeah. For example, if you go here inside the ROS to workspace, which is where we have just created the new Python script. So if you go inside the ROS to workspace here in the code editor and then inside the SRC folder, you are going to be able to see this Python script that we have just created, yeah? And then if you open it, of course, you are going to find that it's empty right now because we just created this file, right? So next step, obviously, is to put some code into this file. And then for that, what you can do is to directly copy and paste, again, the code here from the notebook, yeah? So you come here to the odom distance, you are going to see the code here in the notebook, so you can just copy it directly and then paste it here into the, not like this, we're Control B then with the shortcut, there we go. Okay, So here we have the code in our Python script. Yeah. Okay. Then before executing it, let's have a quick look here at what's going on, right, in this Python script. So what are we doing here? Well, first of all, we are importing some client libraries and libraries messages that we are going to use in our code, in our Python script. We are creating a new class here, which inherits from the node ROS2 class. Yeah. Then in our constructor, we are initializing a new ROS2 node, and we are also creating a subscriber. Yeah, we are subscribing in this case to the odom topic. Yeah, so now that we have the simulation running here, you can, for example, run here a ROS2 topic list command, and you are going to see all the topics provided by this simulation. Yeah, by this Gazebo simulation, you can see here some camera-related topics, the odom topic, also a command belt topic to send velocities to the robot, and a scan topic, which is related to the laser, yeah, and other topics, yeah. So in our code here, what we are doing is to subscribe to the odometry topic, yeah. Then this odometry, yeah, in the case of our simulation, is computed using a Gazebo plugin, okay? Yeah. In real life, yeah, so with the real robots, as you can see them here in the BotBox kit, how this odometry is generated, how this odom topic is generated, is using wheel encoders, okay? In the Gazebo simulation is, of course, we are simulating things, so in this case it's using a plugin, but typically, how this odometry is computed is using wheel encoders, yeah? So what we are doing basically here is to subscribe to this odom topic, and then we have a callback here for the odometry where we are tracking the position of the robot, yeah? And then basically we compare the previous odometry reading with the current odometry reading, and like this we are computing how much the robot has moved over time, okay? Yeah, you can see here that we we are capturing the X and Y values of the odometry, yes? And then we are basically comparing the previous values with the current values. Okay, and like this, here we are tracking the total distance moved from the robot from the moment I start running this script. Okay, yeah, so it's a pretty simple total distance calculation, okay, using the odometry topic. All right, then let's try this program. Let's see how it works. So let's go back here to our notebook. And then let's execute, let's try our program like this. So cd ROS2 workspace SR3, and then Python 3 odom distance.py. We run our program, and then here we can see the current position X, the current Y position, and the distance traveled, which is 0 meters. Yeah. Then in order to see if our program works properly, what we are going to do is to try to move a little bit the robot, right? Then for this, we are going to open a third terminal, okay? Let's open another terminal here. And in this third terminal, we are going to run the very well-known teleop twist keyboard program, ROS2 program, yeah, which basically allows us to send velocities to a robot using the keyboard, yeah? So in this third terminal, we are going to run this teleop keyboard ROS2 program. And then here, let me put this side by side so that I can see my robot moving. Let me come here. I suggest that you reduce a little bit the speed using the Z key, okay? By default, it's 0.5 meters per second, which might be a bit high. So I always like to reduce it a little bit. And then now that I have reduced it, as you can see, the speed a little bit, to 0.26, we can start using the keys to move the robot. So let me start moving it forward a little bit. There we go. The robot doesn't seem to be moving. Okay. Maybe there's some problem in the simulation. All right. Let me restart the simulation because I can see that my robot is not moving here. Probably this is some problem related to Gazebo. Although I can see that here it's being computed properly. See, the distance traveled has increased. But I cannot see it here in Gazebo, so let me just restart the simulation because I want to see it also here in the simulation. Then let me stop the programs here, and then I'm going to just run again the clean Gazebo script to stop all the Gazebo processes. There we go. And once all the Gazebo processes have been killed, I'm going to execute again the simulation launch file to start the Gazebo simulation. Okay, so sometimes this happens in Gazebo, okay, not a big deal. All right, then now let me run again my odometry tracker here. There we go, distance is 0, 0 again. So let me then also relaunch the teleop to its keyboard program, reduce the speed, and then I'm going to start moving the robot a little bit forward. And now we can see it actually moving in the simulation, great. So let me move it a little bit, and then if I go back here, I can see how the distance traveled is increasing, yeah? 0.38 meters, all right? So my program is able to properly, successfully track how much the robot is traveling, yeah? Let me move a little bit more, for example. A bit more forward. There we go. Stop again, yeah? So this seems to be working properly, yeah? And my program seems to be computing properly the distance traveled by my robot, in this case using the odometry data, which is generated using the wheel encoders. Okay? Yeah? So we can use wheel encoders and we can use odometry data in order to track and measure how much our robot is moving. Okay? Yeah? Let me go back. Okay, so what about you? Have you been able to move the robot in the simulation? Did anyone have the same issue as me? Is your simulation working properly for all of you? Is moving, terrible driver. After restart, the robot moves, okay. Same issue, but restarting. Okay, so restarting solved the problems, right? Okay. Daniel says, I can move it. Try restarting the simulation, Daniel. Code editor is not loading. Toshif says, okay, if your code editor is not loading, you can try reloading it with this icon here. Yeah, maybe you can try reloading it like this, or just close and open it again, okay? Maybe try these things, okay? Working here, working fine. To move it, you have to be in the teleop window. Oh yes, that is, yeah, I am overlooking that maybe, yeah. So in order for the robot to properly move using the teleop, you need to have the focus in this terminal, okay? Yes. So if you have the focus somewhere else, for example here, even though you press the keys, the robot is not going to move. Yes? I am right now pressing the keys, but the robot does not move, okay? You need to have the focus here in the terminal where you are running the program. Now, if you press the keys, the robot moves. Okay, this is a detail that maybe I gave for granted, but maybe some of you don't know. Yeah? So you need to have the focus here in the shell where the program is running, okay? Otherwise, the robot is not going to move. Okay, thank you, Alan, by the way, by pointing this out, because I assumed that you already know that, but yeah, maybe it's not the case in case you are new. So yeah. Okay, very well. So we have seen this first example of tracking the distance moved by the robot using the odometry topic. Okay, let's see another example, which is a bit more sophisticated. Okay, let me remember, okay, that this odometry approach is very usual, okay, in robotics. It's probably the most common one, but it has some problems, okay? So, because this odometry, in case it's computed using wheel encoders, it relies on how much the wheels are spinning, yeah? So it assumes that every time the wheel spins, that translates into robot movement, yeah? But what happens is if the wheel is slipping, right? Maybe the robot is on a terrain which doesn't have very good track, yeah? It's a surface which allows some slippery, yeah? Then what can happen is that even the robot wheel is rotating, yeah? It is also it has a bit of a slippery effect on the ground, yeah? Then in that case, the wheel encoder is still going to think that the robot is moving, but the robot is actually not moving because the wheels are slipping on the terrain, yeah? Do you understand this problem? Yeah, and this can happen in some cases, and what this is going to cause is some accumulated error over time. Yeah, does this make sense? Moving in Y direction means moving in the Y axis. Yes, Ali. Moving in Y direction means moving with the Y axis. Moving in the Y axis. Yes, exactly. How can we calculate this? Where in the same way. In this case, that is another approach. I mean, in the case of a differential drive robot, which is this example, okay, the robot can only move in the x-axis, okay? That means forward and backward, yeah? And then it can also rotate over its z-axis, okay? But a differential drive robot, which is this case, it cannot move alongside the y-axis. That would be another robot, which is a differential drive, okay? Sorry, not differential drive. It would be an omnidirectional drive, yeah? Or also known as holonomic. Okay, that is another case, and that would use different formulas. Okay? Here we are assuming that the robot is differential, so it can only move in the x-axis and rotate in the z-axis. Yeah? This robot cannot move alongside the y-axis directly. Yeah, because that would require an holonomic movement. Okay? Okay. Speeding and okay. Yeah, so speed in y-axis is not rotation, okay? Speed in y-axis is another type of movement which requires another type of approach. Okay, that is an omnidirectional, let me write it here, omnidirectional or holonomic. Okay, you can look it around, holonomic. Are most industrial robots moving in just the X and Y axis day to day? It depends. I mean, there are many robots which are differential. It's probably the most widely used approach, okay? But there are also robots which are omnidirectional and use the holonomic approach. Okay, then let's continue. Okay, then because of this problem that I mentioned of the wheels slipping and producing an accumulated error in the odometry, we need to be able to also rely on other sources of information to be able to improve the accuracy of the odometry, right? Then another approach might be using an RGB camera to estimate movement, okay? Then this approach basically is based on this. So we capture the environment and we capture successive images of the environment while the robot is moving, yeah? Then we compare these the successive images, yeah? What are the differences between these successive images, and this way we can estimate a robot's movement over time, yeah? Or displacement, as we say here in this graph, okay? Yeah? So the process basically involves these 4 steps. Capturing successive images from the RGB camera, then converting the images to grayscale to simplify the processing. This is very typical in when processing images, yeah? Then we calculate the absolute difference between consecutive frames, and then analyze the difference to estimate displacement. The larger the difference, the greater the movement between frames, okay? Then, once we can calculate this image flux, we need some calibration tools in order to translate this image flux into actual movement in meters of the robot, let's say, okay? With this example, what we are going to do is to just show the image flux, okay? Then, let's create a new program here. So let's go back to our notebook. Yeah, I am right here. So I'm going to create another Python script here named ROS2ImageDiff. Okay? Then I can close this one already. Here I have my second Python script. And then again, what I'm going to do is to copy the code from here and paste it into my empty script. There we go. Okay? Then, okay, so here we have several things which we can have a quick look at the code, okay? I'm not going to go super into details on the code, okay? You can later analyze it on your own, more line by line, etc. But otherwise it's going to take forever. Then doing a quick overview of the code, what is going on here? Okay, so we have our class, yeah? And then here we have a ROS2 subscriber where we are subscribing to the camera image raw topic, okay? This is the topic where the RGB camera of the robot is publishing the images, yeah? Also, we need to initialize a CB bridge, okay? This bridge allows us to convert images from ROS format to OpenCV format, okay? Because in order to properly process these images, to properly analyze these images, the images from the RGB camera, we are going to use OpenCV, yeah? So we need to convert these images captured by the camera from the typical ROS format, yeah, which is this image interface, to OpenCV compatible format, okay? All right, then in our subscriber, of course, we have an image callback where we are doing all the image processing, yeah? Then basically here, let's have a quick look. So we convert the image using the bridge to CB format, and then we convert it to grayscale, okay? For easier processing, yeah? And then here, we compute the absolute difference between the current gray image and the previous gray image. Yeah. So between two successive images, we are comparing the difference between them. Okay. And then we are also computing here the optical flow. Okay, these are two different things, yeah, which we are going to analyze a bit more in a moment after we have a look at the example, because it's going to be easier to understand. Yeah. So basically, here we are checking directly the absolute difference and also the optical flow between the previous and the current grayscale frames. Okay, these are two approaches which are going to provide us different information. Yeah, we are going to see a bit more on this in a moment. Okay, and then finally what we are doing is to show some displays. Yeah, we are going to show basically 3 different displays. In one of them we are going to show the current frame, so the raw image. In another one we are going to show the threshold difference, which is the one that we are calculating here. Okay. And in the third one we are going to show the optical flow. Okay, we are going to have 3 different displays. All right? Okay, then what are these displays going to show exactly? For this, let's execute the program and let's have a look at how this looks like. Okay, then let me come back to the notebook. If you want, you can restart the simulation. If not, you cannot. Okay, I'm going to restart it just to have everything started from 0. It's not necessary to restart the simulation, but you can do whatever you prefer here. So there we go. Let me restart the simulation from 0. Then here I'm going to run my program with the command Python 3. Let me copy it here properly. Let me get back a bit closer here. There we go. Okay, so here we have our program, ROS to image diff, ROS to image diff. Then let's execute it and let's see what we get. Okay, this is going to take a few seconds to properly load all the displays, and then they should appear here automatically after a few seconds. Let's wait. There we go. Here they have appeared automatically, and here I have the displays. Okay, as you can see, I have 3 displays. First of all, this is the current frame. So this is what the camera is capturing right now. Yeah, as you can see, it's basically this front area of the robot. Yeah, what I am getting here in the current frame. All right. And then here I have the threshold difference, which right now it's not showing much. It's mostly black. Yeah. And here I have the optical flow also. Yeah, which is showing me some colors, etc. Yeah. Then what happens? Let me try to move them a little bit here, put them in different places, make this a bit bigger. Like this, yeah. You can also probably, or can I resize this? Not really. Okay, let me put it like this. Okay, and let me put the robot then here. Let me put it a bit more to the right here. There we go. Okay. And then finally, what I want to do here is to start the teleop twist keyboard program to start moving a little bit the robot. All right, reduce the speed, put somewhere here the displays, and then start moving the robot a little. Let me start by moving it just a little bit to the front. Yeah, let me move it a little bit to the front, for example, and then we should see here already you see how the camera is moving, yeah? Then one interesting thing that you can see here is that while the robot moves, yeah, let me put this here. So while the robot is moving, yeah, you are going to see something interesting happens in this display. Yeah, let me put it here. Let me move the robot a bit forward, or maybe a bit backwards even, see? So as the robot is moving, you can see how these white lines start appearing more, yeah? Then once the robot is stopped, like now, this turns much more black, yeah? I'm going to start moving it a little bit again to the front, for example, and you will see again how these white lines start appearing here, yeah? And something, a similar effect can be seen in this other display. Let me put it here also, yeah? Let me put it here, and let's see what happens, how this reacts to the robot movement. Yeah, let me start moving it a bit forward, like this. There we go. Yeah. Let me move backward also now. There you can see some colors being starting to get much bigger, right? Much brighter also. Yeah. Now I have stopped the robot and this goes down a little bit. Okay. Then what's going on here? What's going on here? Let's analyze a bit more what's happening here. Yeah. Here you can see also the expected result. So in the current frame window, which is this one, what we have is just the raw output of the camera. Yeah. So nothing special here. The threshold difference is this one in black and white, this one here, yeah? Then this one shows a black and white binary image where white pixels are the areas where significant movement was detected, yeah? And the black pixels are areas with little to no change. That is why when the robot is stopped, almost everything is black. Once you start moving the robot, there start appearing areas where the images are having changes, yeah? That is why they start showing in white, because there is significant movement, yeah? Yeah, so this computes, this is the line that we saw here, which computes the absolute difference between the current and the previous grayscale images, yeah? And it highlights pixel intensity changes indicating motion, yeah? Then it converts the difference into a binary image where if the intensity difference is set to white and otherwise is set to black, yeah? So this allows us to visualize where movement occurs, yeah? Based on the differences between images. And then finally we have the optical flow window, which is this other window with more colors here on it, yeah? Then this one has a different purpose, which is to show the motion flow in the frame, yeah? Then this uses an HSV, hue saturation value color model, to indicate the direction of the motion and the motion intensity, okay? Here you have exactly where it is computed in the code. We already saw this previously. It's exactly here, okay? It uses some parameters, okay? I'm not going to go into much detail into this because that's too much detail, yeah? And I'm not even an expert on that. So I'm going to let that part of you to do more deeper investigation, yeah? And then basically here what we see is that the purpose of this visualization is to visualize motion flow across the entire image. And it helps us visualize how objects are moving in the frame. Yeah? Different colors are equal to different movement directions, and brighter areas means faster movement. Okay? Yeah? Two-shift, okay, I don't know about your specific case, two-shift. Probably in your case, you have some kind of plugin in your browser which is blocking the code editor, okay? So if in these specific cases that only one person is having problems with the code editor, very likely it's some plugin that you have there activated in your browser. Did you click on the icon on the bottom? I cannot call it from terminal, so I use that. Why are the colors in optical flow? If robot does not move. Yeah, it still detects some kind of, probably it's some kind of error, okay? Yeah, so even if the robot is not moving, there is still some colors, yeah? The thing is that if you start moving the robot faster, you are going to start seeing brighter colors, and you are also going to be able to see this displacement, okay? But because it is not an absolute difference, like in this one, yeah, you can still see some colors here, some features here, okay? I don't know, Tushif, I don't know. That you need to check it yourself. Visual odometry with camera is very interesting. Yeah, for sure, yeah. Okay, oof, I can see that we are already at 7 p.m. Then let's try to go with the last example, which is using the laser, okay? So we can also use the laser and comparing the different laser beams, yeah, and how they change over time in order to estimate movement, okay? Then here we have the example with the laser scanner, which also it's very interesting. You will see in a moment. And then let's create this third Python script here, okay? So let me create this third one. And then again, same approach is copy the code from the notebook and paste it here in the empty script. Okay, there we go. All right, then what do we have in this specific case? Okay, so here again, we have another ROS subscriber. And in this case, we are subscriber to the scan topic, yeah, which is the topic where the laser is publishing the laser readings. Okay. Then we are going to we are showing some plots here. We are not going to see it so graphical as with the RGB camera, but we are going to be able to generate some plots here to see how the lasers are changing over movement of the robot. Okay. Then here we have the scan callback, where we set the current scan. Okay. We also get the current scan and the previous scan, okay? And then here we are computing the difference between the current scan and the previous scan, as you can see. Okay, we are doing some more things here, but in general terms, what we are doing basically is this, yeah? We are computing the difference between the current scan and the previous scan, similar to what we were doing with the RGB camera, but this time is with laser information, okay? And then using this information, we are doing an estimate of the forward movement, okay? But we are also taking into account the angle of the readings, okay? So the two things. This is why we are going to plot the two things, yeah? First of all, here we are doing a polar plot, which shows the orientation, the angle of the laser readings, okay? And this one shows us the difference between scans. This is the Cartesian plot, okay? Then let's better visualize this, because it's going to be much easier to understand this by seeing and being able to visualize these plots, okay? Then let's execute this program here. There we have it. Okay, I'm not going to restart the simulation this time. Let me just execute the program. And then this is going to show us here a couple of plots. Yeah. We should see it appear here in a moment. There we go. Okay. Then here we have the polar plot of the laser data with the angle and the comparison from the previous scan and the current scan. Yeah. And this is the raw difference between the scans. Okay? Okay, then for example, what are we going to be able to see here? Let's put the robot here. Not this, sorry. Let me put the plot here. And for example, let me start rotating here a little bit the robot. It's hard to put everything here into display. Then, okay, let me try to do it like this. Let me make this. No, this is not going to work. So let me try to put this as to the right as possible, something like this. Let me try to put this over here in the middle. There we go. And then here the rotation. Okay, then for example, I'm going to start rotating the robot now. Okay. And pay attention, for example, here to this plot in the left, where the yellow one is the current scan and the blue one is the previous scan, okay? Let me start rotating here. Okay. These for sure, these fluctuations that you can see here are the error, but here you can see the how the angle is also rotating. Okay. And it allows us to analyze the movement also from the previous scan to the current scan, okay? For example, here we can see that we are also printing an estimate movement, which is the average difference near the front, yeah, in the forward direction. Right now I am only rotating, but if I move the robot in the front direction, I'm going to be able to see also this difference in the linear, in the forward movement of the robot, let's say. So right now we can see this is approximately 0, okay? The fluctuation in the values are because of the laser inherent error in the readings, okay? But let me start moving the robot forward a little bit, and you are going to see how this value is going to be shown here. In this specific code, we are not computing the total distance traveled like we were doing with the odometry, okay? It can be done pretty easily, but you need to add a couple of lines where you basically compute the total and accumulate all the small changes between the laser readings, and you keep accumulating them, okay? In this case, let me just show you how this is going to show here by moving the robot a bit forward. There you go. And you can see here, let me stop the robot before it crashes. There we go. See, here you can see the values start increasing much higher, okay? But then now that I have stopped the robot, it goes back to 0, okay? So what you could do, for example, in order to compute the total distance traveled would be to accumulate all these smaller movements, okay? And in order to do that, all you have to do, I encourage you to try it yourself, okay? You would have to do something like this, something like what we are doing in the odometry code here, okay? Something similar to this, yeah? Where you keep adding the steps to a total distance, yeah? So you would need to do something like this, similar to this in this code, which we are not doing, yeah? It would be something like this, yeah? So we are just computing here the difference from the current scan to the previous scan, and then we are keeping the forward movement estimate and printing here the forward movement estimate, okay? So what you would need to do basically here is to add a line where you are adding all the steps, okay? Because right now we are not doing it, yeah? Okay. what parameters are needed for the calibration? Wouldn't I need some sort of reference measurement for the algorithm to know how to translate the optical flow into actual angular or linear? Yes, exactly. So you are going to need some additional parameters, Daniel, in order to translate this optical flow, as you say, into actual linear or angular movement. Yes, exactly. So here what we are computing is, let's say, units of movement, yeah? In which we call here this flux, okay? This image flux, okay? But in order to translate this into actual movement, let's say in meters, okay, we will need some calibration and some additional parameters to be able to do this translation, okay? So yes. Would it work similar with an ultrasound sensor, just with less accuracy resolution? Yes. Yes, Daniel, exactly. Yes, so with an ultrasound sensor, you could do something similar to this. Yes, for sure. Okay, then we have also here a final example. Okay, there is many more information. Okay, I have skipped many things because of the lack of time, okay? But please, I encourage you to have a closer look at this, at the code, all the explanations that that we have added here to get a more in-depth analysis of all these different methods, okay? Here I wanted to quickly show you a little bit the practical examples and how they work, okay? But now, please, I encourage you to have a closer look at the code, at the explanations, and try to even do changes in the code, okay? To try to improve the code, do changes in the code. For example, for the laser, you can try to compute the total accumulated movement of the robot, like we were doing in Odometry, okay? You can try to do it here in order to improve this computation for the laser example, okay? And then finally, we are providing here this is the more in-depth explanation about the laser code. And then finally, we are providing a template code for doing sensor fusion, yeah? In this case, we are showing a very basic example or template code for fusing sensor from the odometry data and RGB camera data, okay? Yeah, this is just a template, a very raw, basic example, but it's just to provide you something that you can use to continue working with, yeah? Then how this works, very quickly, let me execute this code and show it to you. So I'm going to stop the laser example here and run this one. This example doesn't use the real robot data like the others, okay? All these examples that we have been using were using data from the simulated robot sensors, okay? This final example or template code doesn't. So let me very quickly create this one here as fusion.py. And then I need to just copy and paste. You don't need to execute this one if you don't want, okay? Because this is just a more basic example. And then here we can run it and do this fusion.py, okay? And basically what we are doing here, we are simulating data, yeah, and generating a plot with this simulated data, okay? As you can see, the robot is not running now, yeah? So this is just data that we are simulating, yeah? And then we have some odometry data, which is showing here in blue. We have some camera data, which is shown here in red dots, okay? We have the ground truth, which is in green, the true position, so the real position, and then the fused estimate, which is these red lines that we have here, yeah? You can see that the fused estimate tends more to approximate the odometry data, yeah? That is because in our example code, we are giving more weight to the odometry data. Yes, the weight for the odometry is 0.7 and the weight for the camera is 0.3. Yeah, that is why our fused estimate is closer to the odometry data than to the camera data. Okay, yeah. And this is just a template code with a very basic example to show how to fuse this sensor to generate an approximated output based on the fusion from two different sources of information. In this case, odometry and RGB camera. Okay, then again, you can, this is some template code that we wanted to provide you to give you something to be able to work, to continue working with this project, yeah? So besides analyzing more in depth all these different examples, you can also try to develop a little bit more this code here and adapt it for using it with the simulated robot and with the real data from the bot box simulation. Okay? Yeah? And yeah, as always, we encourage you to share your experiments. Yeah? We would love that you keep building on the work that we provided you with this ROS project. You continue to expand it and you create your own demonstrations, your own examples. And please, if you do so, share it with us because we would love to see that. And we would be very happy to also share it ourselves. All right? Is it also possible to calculate the movement with a cartographer? Yes. Actually, there is a package, a ROS package that does this, which is, if I'm not wrong, is cartographer ROS. You can give it a look. TMND. Yeah. And this package can be used to generate maps, okay, for navigation. All right, then I'm going to leave it here. Thanks everybody for attending the class. I hope that you enjoyed it. I hope that you've learned something new, and I really hope that you can continue working on this project and continue developing your skills. So yeah, as I was saying at the beginning, we are back with the open classes. We are going to be talking about several different topics in the next weeks, so stay tuned. And yeah, so one more time, thanks to all for attending this class. I will see you in the next one, and as always, until then, keep pushing your robotics learning. Bye-bye.